So, hi Simon, welcome on stage.
Hello, can you hear me?
I can hear you very well.
That's
So,
good.
yeah, delighted
Excellent.
to have you.
Right, I will try and use the technology. Excellent. Well, thanks very much for the introduction, and thank you to Lynn for the introduction to our part on OTFT. So today I'm going to talk about our organic thin film transistor technology and describe how we're moving this from a lab-based activity into something which is becoming more of a fabrication facility for making devices. So, as you might imagine, we're a materials company. We're based in Manchester in the UK, roughly central to the UK. And within this building here on floor 8, we do the materials R&D, synthetic procedures, formulation, scale up and development, and some device R&D. Um, the rest of the device R&D and process development is done at the Centre for Process Innovation, which is a kind of UK national lab for printed and plastic electronics based in Sedgefield near Durham in the northeast. So this contains a lot of process equipment that allows us to do photolithography, sputtering, wet etching, dry etching, a lot of the common things that you would do in a display fab line. Um, Obviously, a lot of the display industry is in Asia. So for flexible-based display developments, we are linked with organizations, including Linksil, that Lynn introduced earlier. And we work a lot in Taiwan with the Taiwanese display industry. And there we have a field applications engineering team. And we've recently established a collaboration with ITRI in order to put our materials onto their pilot line at Gen 2.5 scale. So this is for doing pilot scale developments of products that customers in Taiwan would like to produce at a high quality using our materials. So the organic thin film transistor is not radically different from other thin film transistor devices. It has electrodes, which are generally made by sputtering and patterned using photolithography. And then we provide all of the organic materials that go within the organic TFT, including the semiconductor, gate insulator. The SRL is called a sputter resistant layer, and that allows it to go through a conventional sputtering process for the gate. And then we can provide passivation materials and base layer materials, which are kind of inert dielectric polymers, which isolate one layer from another. So we provide all the materials in a formulated clean room package compatible formulation from sizes from 100 milliliters up to 3.3 liters. All the materials are developed with a high performance, so we have charge mobilities around about 2.5 to 3 centimeters square per volt second at short channel devices. And short channel is typically display industry short channel of 3 or 4 microns. They have high on-off ratio. This is limited by the test system, so the actual on-off ratio is potentially even higher than 10 to the 8. They are low temperature processable materials, and I'll go into more into detail about the consequences of that for device applications. And the materials are designed to go on existing amorphous silicon lines. So it's designed to be a drop-in for today's fabrication lines with minimal reinvestments. So compared to other thin film transistor technologies, our temperature of processing can be as low as 80 degrees C, typically below 150 degrees C, but we've demonstrated down to 80 degrees C as a proof of concept. Most other TFT technologies require processing in excess of 300 degrees, even towards 400 degrees. And that is mainly for the PECVD process for putting down the silicon nitride dielectrics, which tend to become worse if you lower the temperature. So hence they're not very plastic compatible, and you have to process the backplane before you're doing the rest of the device. So this is the main differentiator in that we can use this to our advantage, and people can use it for making devices on novel types of plastic substrates or making them devices in novel ways. The process for fabrication uses photolithography via masks or direct photolithography. We make a dual gate device, which includes a back gate and a front gate. We've got various passivation layers and source drain metal patterning. And then we can take this 5-mass process and develop lots of different types of devices by varying the the latter masks and the process. So we've made OLED devices, organic photo detectors, logic. So this shows a kind of zoomed in image of the logic devices, which can be made in an array on, or we can do a kind of multi-project wafer type of application for logic devices on plastic. And then something that I'll talk a little bit more about is mini or micro LED, where we've used the low temperature to our advantage by processing the backplane on top of the mini or micro LEDs rather than attaching the LED to the backplane. So there are a few benefits of low temperature TFT processing. One is that you'll use less energy in the manufacturing, which is becoming increasingly important as electricity prices go up. Um, the substrate type you can use, there's a much wider variety selection of substrates, so you can choose them for their particular transparency. You can have very good optical clarity. You can pick substrates that either are bio-derived from natural sources. They can be biodegradable at the end of use. And also, more importantly, they can be low cost as well. And the last part, which I'll go into in a little bit more detail, is the integration benefits. So we can choose to put the TFT backplane on top of other devices like emitters or sensors, rather than actually processing the other way around. So this, very shortly, this is one of the applications I'll show you within this short presentation, is where we've processed the OTFT backplane on top of micro LEDs rather than trying to attach the LEDs to the backplane. And this does potentially get around some of the transfer losses and reliability of attaching these microscopic LEDs to the backplane. And so this is the first demonstration we did in conjunction with Shanghai Jiao Tong University in China. And there was a paper towards the end of last year in Nature Communications describing that work where we've made these small arrays. So this just shows two videos, one of a mini LED backplane and a micro LED backplane at 25 ppi and 254 ppi, showing the working display. They're fairly low resolution at the moment, but these are just kind of proof of concepts, allowing to show that we've not harmed the LEDs during the fabrication process of the backplane. So this potentially can go to higher resolution even than this. We've just demonstrated 508 ppi. With the right lithography, we could get up to 1000 ppi. And the brightness can be engineered to be quite high. So even though these are current-driven devices, the OTFT can be expanded to give over 500,000 nits in the ideal case. But one of the disadvantages of that way of processing is that the cost of the display is the cost of the area of the gallium nitride that you use, and hence it only applies to very few small markets which can tolerate that high cost. So the next development that we're doing is to be able to use a hybrid of the current pick and place process, where you would space out the LEDs from a source wafer onto a transfer sheet, which is a kind of an intermediate carrier, which can be much larger than the wafer, and therefore use much less of the LEDs per area, and then build the backplane on top. And so this is just showing very briefly the first kind of experiments to show that we can take spaced out LEDs and then put down a insulating layer, which we develop ourselves, bias through, and then sputter contacts down onto the anode and cathode, and then light them up to show that we're getting a good electrical contact. And so we've done this with both 110 by 60 micron LEDs and 20 by 35 micron LEDs. And so this just is a very short animation to show the whole process in terms of how we envisage it and how it potentially could be an alternative way of manufacturing micro LED, which potentially will get around some of the low yielding steps. So this is the source wafer with your LEDs patterned. These would then get transferred on a kind of a one-to-one onto a separate substrate. So the pads on the LEDs would now be facing the carrier substrate as shown. These then need to be spaced out. So then there'd be a process of using a laser transfer process to transfer selectively, say 1 in every 3, 4, 5 LEDs onto a much larger sheet that then can be processed afterwards. So these now have got the LED pads facing upwards. The space out so we can take a single wafer and transfer it over to a very large substrate. We then need to planarize out the LEDs. So we deposit a planarization material, spin coat it, and cure it. And we make vias in those and metallize those to form contacts, the anode and cathode, and then we can then build the backplane on top of that. So the rest of the backplane process is a series of photolithography steps, similar to how we process the original wafer, as shown in a couple of slides earlier. And then at the end, you can potentially even have a flexible transparent display, because the transfer sheet itself could be a laminated plastic on glass. And so then we can remove the whole thing off and make a fully functioning display. So some of that's animation, but the work is currently ongoing to realize these practically and try and improve the process in order to make it high yielding and low cost. So in the end, this is the last slide. Just to summarize that we've got a lot of R&D work, which is at 4-inch or 8-inch scale in the UK. For that, we use digital lithography, so we can have a fast turnaround of different design concepts. And we can do the key learning to get the proof of concept working for the various applications of the OTFT. We're also doing logic devices, currently PMOS, but we're looking also now to expand into CMOS using an N-type device in conjunction with our P-type in order to get low power and greater reliability. Then Gen 2.5 scale, as I said, we're transferring the process into ITRI, which then will improve quality, and we've got AMOLED projects which will produce displays in the next year or so to demonstrate the usefulness of that process. And following that, it then will transfer into production lines from ITRI, which then can go from Gen 2.5 to larger size substrates, and we can also incorporate new types of display formats, and those will then go on probably in around about 2026 onwards. Okay.
Nice. So let's see if there are any questions. So how many, what are the number of cycles that your TFTs could work efficiently?
We haven't done very extensive testing on sort of cycle testing. We tend to do a lot of bias stress testing, where the device will be biased at a particular potential for several hours. We normally increase temperature to maybe 60 degrees C, and then look at the cycle of the device turning on and off to see whether there's any change in the electrical characteristics. The materials or the devices themselves are quite stable. We've done kind of long-term storage stability tests where we've tested them after sort of 2 or 3 years and seen very little change in performance. The actual kind of biased in the on-state test, we've done several hours and tried to extrapolate these changes over a longer period of time. But it's certainly something we probably need to do more of, is to look at reliability of switching and constant current driving for long periods of time.
Very nice. Another question I have is, so when looking at the architecture of the micro LED system or the mini LED system, you have the micro LED, and then next to it on the top you have the TFT. Would that not limit the pitch and the PPI? And how big do your TFTs need to be in order to provide sufficient current, to get the right, brightness?
They don't need to be as big as you might think. So we've done demonstrations of several tens of thousands or even hundreds of thousands of nits with TFTs that fit within pixel sizes of, say, 50 or 60 microns or so. We can emit light downwards, so we can actually build the TFT over the whole entire footprint of the pixel. Because we put in the LED first, we can reflect all the light downwards, and therefore we can make use of the whole architecture. So it's not a case of we have to have a separate part for the LED and a part for the TFT, where you then have a kind of an aperture ratio. So the advantage of building the TFT on top of the LED is that you can use the whole area of the subpixel for putting down your circuit, and that then gives you some advantage versus if you have to put the LED on last, you then potentially will not want to solder the device on top of the LED on top of the TFT, because it might damage the TFT.
Very nice. This is a very innovative solution. So another question is Is the laser transfer process mature in micro LED? I guess that's what you're trying to avoid, but maybe you can
Um,
comment on it.
I mean, we don't completely avoid transfer. That's the thing is,
Hmm.
building on the monolithic wafer would avoid transfer, but then that has that inherent limitation of you've got to buy the whole area of the wafer. So we're not advocating that that is the way forward. You have to do some transfer from that wafer onto something else. What we're saying is that you don't need to do the laser welding of the contact pad of the TFT to the contact pad of the LED, which is one of the lower yielding steps. I'm not saying that the whole industry is mature for laser transfer of the micro LED. There's still lots of challenges involved with that. So somebody has to kind of perfect the way of taking a high density wafer and then exploding it accurately to positions that then you can have your display on. So it's not everything solved yet. That's correct.
And in which laser wavelength did you transfer the micro LEDs? And do you make the TFTs after the micro LED transfer?
We've had two ways of transferring. One is with using UV laser, and the other one's using a visible laser. I'm not sure which one is the best one to do yet. The visible laser is probably a much lower cost system. There are other ways of transferring which don't involve lasers. Some of them use UV exposure. And then you can also use things like stamp transfer as well. So I don't know yet which is the best way of doing the transfer process. That may turn out to be the best one in the future. But we do build a TFT on top of the LED. So we have to planerize out to make it nice and flat, then build wires down to the contact pads and then build everything up. But it's not so difficult to do with the right materials. So
Another question is, you mentioned lithography and at the same time look for environmentally friendly processes. Have you tried additive processes for the electrodes?
not recently. No, I've tried it in the past with other companies, but the main challenge with additive printing is the overlay accuracy of one layer of the device to the other. You can get very high resolution with things like reverse offset printing down to even submicron, but it's actually kind of, if you're going to do these things on plastic roll to roll, then plastic will distort massively. And so therefore having the ability to align with a kind of almost micron, you basically have to align with sort of 1/4 of the precision of your smallest feature dimension in order to get the device to work very effectively. And so I think that's the main challenge with printing, is not the printing necessarily, it's the alignment of the next layer of printing, because it's a multi-stage device.
Yep. Very nice, Simon. Thank you so much for the very nice presentation, for answering the questions. I think if anybody has any further questions at the break, you'll find Simon at his little kiosk, at his little virtual booth.